Welcome to our third and final Fireside chat for this edition of Search with Machine Learning. I'm really excited to welcome Ram Sriharsha, his name I hope I pronounced correctly, VP of Engineering at Pinecone, which is a fully managed vector database that makes it easy to add vector search to production application. It combines vector search libraries, capabilities such as filtering and distributed infrastructure, to provide performance and reliability at scale. And before joining Pinecone, Ram was VP of Engineering for Splunk. He was previously at Databricks and Hortonworks, so he certainly knows his way around big data stacks and making them accessible and analyzable. He studied at the illustrious IIT Madras and has a PhD in physics from the University of Maryland. So welcome to our class. And just so Ram, they're just in the final week where they are in fact studying vector and neural search, so are very primed for today's topics.
Very cool. Great to be here.
Yeah, Ram, and thank you so much for joining us. Let's kick things off. And as always for our students, please feel free to use either the chat or the QA feature if you have any questions. We love to have student questions throughout these fireside chats, so it's not just Daniel, Ram, and myself having a conversation. So maybe to kick things off, Ram, I'd just love for you to get us up to speed on Pinecone. Like, what is it trying to do? Who is it trying to address? Like, what are the main use cases? What are the main features? What are the differentiators?
Yeah, great question. So first of all, I think Daniel covered what Pinecone does in like one sentence as efficiently as I could have put it. So we are basically a SaaS managed platform for vector search, which means customers who come to us come to us with vector embeddings. We act as a data management platform for that, but as well, we allow them to do scalable search. Okay, so in essence, what they do is something called nearest neighbor search, and nearest neighbor search over these vectors is supposed to give them semantically relevant content. That's the main reason why they use a database like Pinecone. We are the first fully managed vector database for vector search. Okay, why do they come to us? They come to us for multiple reasons, and these are also the areas where we focus very heavily on. First of all, ease of use. Pinecone is extremely easy to use today. In fact, that's one of our big focus areas, and that's also where we see a lot of people really being successful when they start with vectors. Vectors are still new for most people. So even though they may have heard that vector search can really significantly enhance their search capabilities, they're starting with something very new. So first, they need to be able to experiment with things and to make sure for themselves that this works and there is value here, right? And that 0 to 1 step of the journey is about as easy as it gets anywhere in Pinecone. Okay. Now that said, we are continually improving it, so we want to be the best at what we can do here. But this is already like a huge differentiator, right? So people are able to come to Pinecone. They're able to spin up a small machine. In fact, we have a free tier, so you can even play with data for free, right? If it's small enough that it fits your workload. In fact, some people run stuff in production on the free tier, right? So that allows you to easily kind of evaluate for yourself that Pinecone works for you, right? In fact, vector search works for you. And then from there, you can easily kind of scale up, which is, again, really hard when it comes to even ordinary, regular databases. This is actually a hard problem, right? Being able to scale up from 0 to 1, going from 0 to 1 to 1 to n is really hard. We have done this for vector search, which is fundamentally a hard problem as well. So just the ease of scaling up, the ease of going from kind of testing your workloads to actually running them in production at scale is about as good as it gets anywhere today. So Pinecone does it as well as anyone can do it today. The last area where we focus a lot on is if you look at open source libraries, if you look at what many of our competition does, vector search is very hard for a lot of people, because not only do they have to know that vector search is useful for them and figure out how to kind of integrate it into their existing workflows, they also have to tune the system very heavily, right? They have to figure out what sort of vector search techniques even work for their data sets. They have to understand how to change things when they go from a certain scale to a 10x magnitude and so on. So they're spending a lot of their time just figuring out the distributed infrastructure, figuring out the tuning, ensuring that they have high recall and all of this. What we offer are operating points. So basically, if you're operating at a point where you don't need very low latencies, you just need to store a large number of vectors and you're running queries every now and then, you just pick a particular operating point that we provide. You don't have to think about tuning the system at all. It's self-tuned for that, right? Likewise, if you care about very low latencies or very high QPS, as often product recommendation or retail recommendation systems have to work at, you just choose that operating point, right? So you're no longer fighting infrastructure, you're no longer figuring out how to scale things on the cloud. You're not figuring out how to get the highest possible recall for the amount of cost or the parameters under which you want to work. So this is roughly the three areas where we shine and where we kind of put a lot of our focus. Now, underneath it is a very complex system that really just has to scale on all these dimensions. But at a high level, this is what we focus.
That's really great. And I mean, certainly, anticipates obviously the question I was going to ask about, how you see yourself as distinct from the open source approaches, like, I guess, Face being the obvious one, which I say, to your credit, you have a great explanation of on your company blog, or tools like Vespa. What I am curious about, even stepping back a bit, who do you see as the folks who should be diving into vector search? Maybe to preface that, right? Most of the students in this class are search professionals, and they work in search, but probably with stacks that are, essentially they're Lucene based or equivalent to inverted index ones. This feels like a time when people have to decide, do I do vector search? And how do you think about it?
This is a great question. First of all, I would say that in some cases it's somewhat inevitable, meaning there isn't any better way to do this. For example, if you're trying to do near duplicate detection of images, right? You want to know whether some image is a near duplicate of something in the corpus. There is just no other way to do it today. This used to be something that was super hard to do, and people wouldn't even attempt doing it, or they would use image metadata and somehow try to convert this into a structured query that they could run on. But you couldn't fundamentally actually compare images and do anything meaningful. But with vector search today, you can actually do this. You converted what happened to be a very unstructured question on a very unstructured piece of data into a very structured question on proximity in vector spaces, right? So there is a class of these sort of applications which simply get unlocked in a way that you could never do before. But even if going back to your example on lexical search or what's called keyword search, imagine searching for soda, and you want to show Coca-Cola, right? Now, Coca-Cola is not a keyword that has anything to do with soda, right? And there is no keyword match between these at all. But semantically, it's kind of obvious that these two are related. So a semantic search engine would be able to actually pull these together and correlate them in a way that lexical search engines like Elastic or any of the other traditional Lucene stacks and all of them cannot do, right? So even in traditional keyword search, there is a lot you can augment by adding vector search today. And in fact, your popular search engines are already doing this. Many people are already doing this. What Pinecone does is just enable it at a scale that wasn't possible to enable before. But if you go beyond this keyword sort of text search into whether it is time series anomaly detection, or whether it is, like I said, image search or image deduplication and so on, those are areas that are completely kind of unlocked by these new technologies in a way that they weren't before. Yeah. So short answer, I would say, is start with areas like text search, where you know that you want to augment your existing text search capabilities with something like semantic search. But long term, I expect enterprise search itself gets disrupted by technologies like this.
You mentioned earlier, as you were describing Pinecone, Ram, that, find out if it works for you. Like, what are your recommendations for how, professionals evaluating these engines should find out how it works for them?
Absolutely. First of all, I think the pick use cases that are important for you. So because you have to invest some time in experimentation and so on. So you want to start with a use case that's very well defined and where you know that you're not getting the value you need in your current legacy systems. Come to technologies like Pinecone, which are SaaS products, which make it very easy for you to ingest your data. It has a Python interface, so you can. Among other interfaces we support, Python is probably the most dominant one that people use. It makes it easy for you to experiment also, right? So you can actually ingest data. You can pick a set of terms or a set of queries that you want to search on, and you come up with recall metrics, so the metrics that you care about, and then just run a comparison. We make it super easy for you to do this. And we bias towards recall, which means we try to provide you the best recall possible, even if it means slightly lower search, right? Slightly slower search, right? So we always bias towards higher recall, which means you get your best results here. And all you have to do is to decide whether that works for you. And then you can start scaling things out or up as you want. Okay. So that part of the journey, I would start by just picking the problem that's most closest to what you want to solve. One where by looking at our documentation, for example, you can map it to something that's already been solved. For example, if you come to Pinecone's website, there's extensive documentation on different sorts of problems that have already been shown to be ripe for disruption with vector search. Now we are adding to this corpus on a daily basis, right? On a daily basis, we are finding new use cases that even we didn't know before. But you want to start with things that have been well established that you get better results with vector search, and then just kind of experiment from there.
Yeah.
The other thing I would say is sorry, go ahead.
No, you can complete your thought. I was going to follow up.
The other thing I would say is we have a strong community as well. So we are active in the Slack channels, and we answer community questions and so on. So if you have a use case which is not immediately apparent that it works with vector search, just shoot us an email. Chances are that one of us can help you there.
Excellent. So if we think about the evolution of sort of getting search technology back, that obviously in the older days, everything was sort of built themselves, and then you'd have these back in the day on-prem products, but then you start to see the Google Search appliance or Swift type or Algolia, and it roughly, I'd say, attempting to say, hey, just plug your index in and it will just work. Now we know that that's not exactly true in the sense that you typically have to think about your fields, you have to do a few things, but they've tried really hard to minimize this. What does that path look like for using vector search?
That's a great question. I think, so by the way, while I've been talking about vector search a lot, Pinecone recently released something in private preview that's called hybrid search that actually combines the best of vector search along with the best of what we call sparse retrieval, right? So I do want to say that it's, we kind of do both. That said, I think you're 100% right. When people were looking at traditional legacy search engines, because it was keyword search based, you actually had to do a lot of legwork on top, right? So just thinking about the keyword search engine, it's not good at fuzzy matches. It's not good at a lot of, even kind of weighting that's very dependent on domains and things like that, right? So it's a lot of things it had to push to the user. You're finding that it's increasingly less and less of that you need to do in vector search. But what it gets replaced by is better models. So a vector search is about as good as your models are, right? So the quality of the embeddings is at the end of the day what decides what is considered semantically relevant. So in some sense, it gets pushed to these models. But what's really interesting about these models are, especially the ones that are popular these days, after years and years of work on them, they've gotten to a point where pre-trained models are very, very good for the 80% use case, which is surprising, but also really unblocks a lot of use cases, right? Because you don't have to spend that much time kind of feature engineering and actually doing a lot of the legwork that you used to do in legacy search engines. Yeah, and that's a key part. If that wasn't the case, vector search wouldn't have taken off the way it has taken.
I mean, following up on that, maybe putting a little bit more of an engineering hat on that, like, what does my stack typically look like? Like, am I sending you the things that I've already run through Hugging Face? Are you providing the pre-trained models? Like, what does the round trip of both indexing and search look like for people on this? Obviously, you mentioned a Python client, so that part's pretty straightforward, but paint the bigger picture of an implementation, if you will.
Yeah, that's a great question. Today, customers of ours send us vectors or embeddings, which means they have models on their side that either they're making API calls to OpenAI or Cohere or Hugging Face and so on. They get these embeddings from there, and then they send it to us. Okay, so these embeddings are created once, but they're used many, many times over. That's why they need a database where they want to store it and search over it and so on. So their stack often looks like some sort of Lambda functions or something that's running in the cloud that is creating these embeddings by making API calls. And then we have a lot of documentation on our side that helps people to figure out how to integrate with these partners and people like that. We don't actually host models ourselves. There are a lot of good places that do that today. Hugging Face is a great example. OpenAI is a great example. Cohere is a great example for NLP models and so on. So we don't necessarily do that. What we do is to make it easier for people to get that data in and get value out of it. So their stack is usually kind of some sort of cloud functions doing this.
Yeah.
In our case, we provide Python APIs for people who are very familiar with Python and comfortable with it. That said, we have REST APIs, we have gRPC clients, like a bunch of things that people typically tend to use in production, which is not necessarily Python.
Yeah, fair enough. And yeah, I mean, certainly folks in this class will be quite familiar with the sort of Python setup, whether they signed up for it or not, because as you point out, that's kind of the lingua franca for, at least for
Exactly.
in dev.
Yeah.
So I'm curious with these pre-trained models, one of the challenges that we've run into is that they're great for document similarity, right? If your input is in the same space as, and your image similarity example is much like that. But for cases where you have queries that say, particularly say short queries and long documents, we know that there are 2-tower models, a variety of strategies. Yes. I'm curious what you find people using, especially given that you're working with folks who aren't necessarily kind of AI experts as they're building this.
Yeah, absolutely. I mean, I would say that the dominant, I would say that the dominant mechanism is still pre-trained models, but I would say that about 25% of customers actually end up fine-tuning models, right?
Okay.
And creating these 2-tower models and so on. Very, very few customers actually train an entire model from scratch. It does happen in very specific domains, where they have a lot of data and data science teams and so on, but it's very uncommon as far as I have seen. It's far more common to do fine-tuning. Yeah.
Maybe you could, go ahead, follow up.
Yeah, so and I'm glad that aligns with what we're encouraging folks to do for lots of good reasons. I guess, I mean, I'm not aware, for example, in the case of the 2-tower case, that you can ever get it pre-trained, right? You have to do some, at least fine-tuning yourself, but that, are people able to, in particular, say, map search queries to vectors using the same models that they're using for their results? Because that's something that we do in the project work for this week, right? But it tends to be a little bit discouraged in production for what we've seen.
Yeah. First of all, people tend to use query models and embedding models that are separate. So you actually train models for queries separately. Sometimes they can use the same model, but that's not very encouraged, right? But if you go down that route, you need training data and you need to be able to fine-tune models and you need to spend time doing this. And definitely we see lift in recall and things like that if people do this. So it's very, and what is nice, I think now is there's a lot of documentation, there's a lot of help you get in how to do this. So it's fairly accessible, I would say, these days.
Yeah, I've got all kinds of engineering questions, Ram. I mean, so you mentioned you just released and now have and support a hybrid model. We had
I would say it's in private preview, so it's not public preview. What we did was we private previewed it, and now we're collecting feedback and using that to typically before we go GA, we have a period where we actually collect feedback and really work very closely with customers, and that helps us shape what the product should look like.
Gotcha. Because I think one of the questions the student has, so I don't want you to have to give away any proprietary information there, but I think one of the student, a lot of us are like, hey, when do I go hybrid? When do I go vector? And when do I blend? And then how do I blend? Yeah. We literally had these questions come up in discussion this week. Curious to the, obviously Pinecone has a solution here, but curious as to how you think about those problems.
That's a great question. So our hybrid search is really currently focused on enhancing vector search with sparse retrieval, right? So basically there are cases where sparse retrieval, because of its specificity, kind of picks out certain documents much better than dense retrieval does. Dense retrieval does great at semantic similarity, right? There's still some areas where sparse retrieval is really good. What people have been doing today is kind of having 2 different engines, which is like a dense engine like Pinecone or some technology like that, and legacy search engine. And they would kind of issue queries to both, and then kind of pick the top certain number of results and try to re-rank on their side, right? First of all, this is not very efficient. This is far more operationally challenging for them and also costly for them. But it also doesn't yield the best results, right? Because the fact that you pick 100 or 1,000 documents from the result set of these two things and try to re-rank doesn't necessarily give you the right top 100 or the right top K, right? This is where, and more customers were coming to us and with that problem. And we decided there's actually a better way to solve it if we try to have the dense and sparse engine kind of together and do something that's better from that perspective. That said, we still do something morally, you can think of it as the weighting between sparse and dense scores, right? Except it's done by a single engine. Okay.
So is the user having to decide when they want hybrid, or are you doing that automatically?
We're doing that automatically. We do that for when they have text search, they use this hybrid engine. When they have traditional dense vectors, they use the dense engine. Okay. By the way, even outside of keyword search, there are models these days that are sparse, producing sparse vectors. So you can think about doing that as well, which is just having a pure sparse engine, right? So to some extent, this is a bit of an art when it comes to outside of text search, right? It's a bit of an art to say when to use like a sparse engine, when to use a dense one, how to blend the two together. It's still a bit of an art. So we are still figuring out how this should exactly work. But for text, it's somewhat better understood.
Well, so that's a perfect setup for my next question about what's an art, which is basically everybody understands that, cosine closer to 1 is better, lower is bad. But lots of people, myself included, have wondered, how do you decide how high a cosine is good enough to include? You said that you favor recall, but I think you were raising the computational issue. And I think that it's not just the computational challenge, but especially whether you're doing this kind of a rank fusion or other things where the set matters. How do you sort of go about in a particular application tuning what kind of a threshold? What's the process?
Yeah, that's a great question. Today, we don't really allow you to tune much. The way you would tune here is you would pick the metric. You would say, I need cosine as a metric, but then you pick the top K and say, I want a top K of 1,000 or top K of X and so on. That's kind of the proxy for how far in cosine distance we go, in a sense, right? How far in that score we go. We don't really allow you to control like get me by distance sort of thing, right? So that's something that's been a feature request. We are looking into it, but today we don't do that. Okay. We also allow you to control recall in some sense by very few tunable parameters. We tend to not allow people to tune this because it's hard for people to understand how a tuning parameter here affects scale, memory usage, and all of these things, right? Fundamentally, approximate nearest neighbor search is trading off computational intractability or tractability for recall. So that's allowing too many knobs here actually might make the situation worse. So we don't really allow too many knobs here, to be honest.
And maybe that,
go ahead.
Well, I was going to say maybe that feeds into explainability in search is often something that comes up, and I'd be curious to hear your thoughts on that, or what support Pinecone has for those kinds of things, especially in the context of engineers debugging search, not so much end users like understanding why 1 is higher than 2 in the result set. Yeah,
that's a great question. The thing we do today is we retrieve the scores, the exact scores, to actually know what the exact scores were, and our algorithms have a fairly tight bound on recall. So for a given setup, your recall is not going to be lower than a certain number, and we keep this number very high. That's why we said we bias on recall. We want to keep the recall very, very high. And when I say very high, it's much higher than what you would get in most places. Okay. So in some sense, when people come to Pinecone and run experiments, you typically find much higher recall than you would find anywhere else. Okay. However, the best way today that we have in all of this is actually just letting customers experiment. We make it easy for people to experiment and compare against recall metrics that they would have from the single node experiments or something somewhere else, right? That's the best we have today. We are thinking about what we can do to provide better metrics here, but I think we're still in very early stages in terms of that sort of debuggability for vector search. I would say that it's not a solved problem today.
So go back to the sort of approximation and question. So JJ asks, different applications at different precision and recall targets, or perhaps computation requirements. And like, I know that, we talked a little bit about it in our reading this week, that you can use quantization, you can vary the vectors, you can obviously vary the parameters a bit in the approximation. But as you pointed out, that's a lot of stuff for most people, even experts, to understand. You said something about operating points. Is this how you?
100%. Yeah. So if you think about it, right, people play around with all of this because it's not because they want less recall. It's simply that they want something that's easy to operate and cheaper and cost effective for what they're trying to do. Ideally, they would want the best recall possible because that's really what the value proposition of vector search is. But to get the best recall with exact search, it's computationally gets intractable past a few million vectors, right? So the result of that is people are playing around with all these quantization methods and so on. We just don't want them to play around with it. We want them to let us figure it out for them, right? Because A, that's easier to, especially for a managed service, that's the only way to build it. And B, by providing these operating points, we can do that in a very consistent way. For example, if all you want to do is search over a small number of vectors, your corpus doesn't ever grow much bigger than a few million vectors, but you have to run tens of thousands of queries per second on them, and you have to update this corpus very often. That's one operating point, right? That's really in somewhat smaller scale, even mid-scale recommendation systems often end up doing that. That's a very different operating point from having to store a billion vectors, search over them, where you don't really care about latency as much as long as it's in the hundreds of milliseconds, right? In the one case, you may care about 5 millisecond latencies. In the second case, you may care about hundreds of milliseconds, but not very high QPS. And you are far more interested in storing a much larger corpus, right? And then there is the final stage where you're just running on-demand queries. This could just be for some labeling tasks, right? You just want to spin up a query and just run it on billions of data points. And you do this once in a while. Now, these are very, very different operating points, right? And you don't necessarily want to tune one system to try and achieve all three of them. What you want to provide is these three different operating points, where within those operating points, people don't have to think about recall at all. You get the highest recall possible. The way the indexing technique we choose and how things are laid out, whether it is on disk or whether it is in memory or whether it is kind of on blob storage and so on, all of that is controlled by us, right? The mechanism of distributing those fragments of those indexes is controlled by us. The mechanism of concurrency is controlled by us, right? That's what we do. So we provide these operating points, and within these operating points, there's not a whole lot of dials you can choose, but you get the best recall possible for the lowest cost possible in these operating points. So that's our solution to this problem, which is we don't necessarily want to move this problem to the customer because we feel like that's not the right solution. The right solution is to provide these operating points that are fairly distinct. So when people come to Pinecone, they kind of know which operating point they're in, right?
And reminder for everybody, please do ask questions. JG, thank you for that one. Ram, maybe shifting to like the actual application building. I mean, I think one of the things, I think we all know we're in the early stages of these vector databases, and yet at the same time, there's kind of been some standards developed around search, things like faceting, spell checking, query understanding, like re-ranking, et cetera. Like, how do you think about the whole application and where vector search fits in that? And you know, what of those things of what we would call search features does Pinecone support? And if you don't support them, what do you typically see customers doing for those things? I know that's a lot there, but tell me about the application.
Yeah, that's a really great question. Pinecone doesn't support faceting, and we have internally discussed a lot of these topics. So today we don't support faceting. Today we don't support a lot of what's kind of the application facing side of search. What we are really this kind of fundamentally a database for this sort of sparse and dense retrieval. That's really what we do. What I expect to happen over time as this area of vector search really gets refined over the next few years is databases or technologies like Pinecone will provide the primitives that you use to build search applications on top. So we won't actually enter that space, but we provide these primitives. For example, for us to do aggregation or faceting very efficiently, there are some primitives we have to provide you, right? That gets baked into the database and baked into the sort of system that makes it efficient for you to do this without having to move too much data around or keep a dual copy of the database and so on. Those are the things we focus on. But fundamentally, we just focus on search over sparse and dense vectors.
Yeah, I mean, I think that's been the challenging on the engineering side is like, things like faceting, aggregations, et cetera, like that's an inner loop calculation often, or you need the bit sets that have all the IDs and so as you're iterating. So if I'm understanding correctly, like those kinds of things a user would have to do by pulling out back the data and then doing it on their own.
Exactly. And we provide some things for them. For example, you can retrieve vectors along with the IDs today, right? So there's some data that we provide for you. For some, we are providing a path for you to get that data. But regardless, I think some of these are external concerns to this sort of a system. What I think will happen over time is that there'll be layers that kind of get built there, right? And people will end up using it. There'll be probably one provider that provides that. But today, I think it's still very much a work in progress. It's part of the set of features we still don't fully understand about what the sort of vector search systems need.
So I'm curious how you address kind of an engineering challenge that can happen as people combine these things, right? With an inverted index, probably the part of it I value the most is that because you have sorted lists that are all using the same sort, it's very easy to do the kind of traditional set operations, ands, ors, what have you. But obviously with the nearest neighbor list, it's never going to be in the canonical order because it's the distance.
Yes.
And combining that seems harder, but I know that you do support some ability to do that. I'm curious to the extent that you can share how you manage to do that efficiently.
Yeah. So if you think about these sort of set operations, that they're usually for filtering, right? They're usually for narrowing down the scope of the corpus that you want to look at. And we support conjunctive and disjunctive filters today, but we do it through this notion of filtering. If you think about filtering, even if you gave that ability to customers, it's actually hard for them to do it today. Meaning, suppose filtering was external to this sort of a system. What you would have to do is you would have to just search over, get some certain top K, and then try to filter it on your side, which would be what we call post-filtering. That's actually error-prone, right? Because it could happen that nothing is actually retrieved at the end of the day, right? You can also do filtering prior to search, which is you can run your corpus through the filter and then send it to a search system or something. But that's very inefficient, right? Because your filters can be highly selective and you end up with these tons and tons of indexes that you have to manage, extremely ineffective. And even if we did that on your side, if we did it in a pre-filtering sort of approach, we kind of lose the index in the first place, right? So the real trick is in being able to kind of filter while searching, right? And that's what Pinecone calls metadata filtering. We did it first. Now there is sort of other competitors who are starting to do it, but we did this about 2 years back. And this is really the hard part. A good example is when you're doing graph search, right? Graph search is greedy search. You start from like a greedy point in the graph and start to traverse the closest distance from there on. If you think about doing that, what you want to do during filtering is as you're traversing this, you want to decide, are each of these points that I'm seeing passed by the filter or not, right? That would be like filtering while searching. Okay? Yeah. The biggest problem there is, of course, it could happen based on how the filters work, that you have to traverse practically all of the graph before you end up with points that are viable, right? So if you don't do this well, it can be just about as inefficient or even much worse than exact search, right? So the real trick is actually doing this not only correctly, but also in a computationally fast manner. And that's what Pinecone does.
Yeah, I mean, this is, I think, Lucene and Solar and Elastic, like this was probably the bulk of work that those engines did. Right. And then recognizing that these filters can then be used for faceting and all of these other types of aggregations, as long as you build some supporting memory structures to go with them, right? And that's in many ways been the story of the 2010s for those Lucene-based engines. And sounds like you all are on that same track as again, but you'll have the benefit of accelerating it because you've seen how it's been done.
Absolutely. I think for vector search, it's still more complex than inverted indexes. In some sense, inverted indexes are fairly natural for this sort of conjunctions and this sort of filters. With vector search, it's actually harder.
I mean, there's precedent in very low dimensional, if you will, vector search with things like geospatial indexing. But there, of course,
Yeah.
it's a lot easier to just say you break things up into regions and
Yes.
those regions are canonically sorted. You can't do that quite so simply with
Yes.
very high dimensional.
100%. Yeah. At the moment you get past a few dimensions,
Yeah.
even out of 5 or 7, I think it becomes much harder to do this.
I think Matthias is asking a related question. This one actually, I think, sets up a little bit better for vector search than say the faceting, which is what about suggestions, autocomplete? In many ways, those are just yet another search. So I would imagine that particular use case lands pretty well.
It could. Again, today our focus is on vector search as an infrastructure. So we aren't really super focused on text autocomplete and these sort of features. We're looking at features that actually translate these domains, right? Whether it is text, whether it is images, tomorrow it's time series data, right? So 100% agreed. I think this is a very natural kind of feature that these sort of engines can support. But we aren't that primarily focused on just text search. We're looking for things that translate across many different domains.
So, in the context, again, we have obviously a very search focus, but this you could imagine even in the case of recommendations, it's often the case that you've got what amount to query dependent and query independent factors. And in the case of search, it would seem that the similarity of the vectors is a single scalar encapsulation of query dependence, and everything else might be query independent. But
Yeah.
there are certainly folks who try to use a richer query dependent notion, maybe even the entirety of the vectors themselves. I'm curious what you're seeing in terms of the way people do this, because obviously the first approach sounds really simple. The second approach sounds really complex, but
Yes.
a scalar is a pretty small representation.
That's a great point. Today we see the first approach, but I think that's more because that's the simpler one, and that's what people are. People are doing. I haven't encountered the second approach personally in terms of our customers, but it's a great point. I think you're 100% right that it's a kind of scalar notion that probably won't capture everything you need to capture. But I wouldn't even know how to do the second one today. Like it's.
Well, then as a follow-up to that, it comes back to this question as to what the cosines mean. Like, do you see that, depending on how people design things, maybe the cosines are just very densely clustered around, 0.98, and you're like, it's 0.9799 or 0.9801,
Yes.
or wide spreads. Is this something people have to sort of engineer?
That's a great point. I think it is more widespread than you would think. So I think it turns out to be far more widespread. But this would just be a little bit of a hunch, like meaning it's one of the areas where we are actually collecting more data to figure out exactly how things look here. One of the advantages of being a SaaS platform is you can actually look at data and analyze this. But this is my preliminary hunch based on kind of seeing what's happening in production and kind of how people are taking advantage of these sort of systems. So it's just a hunch from looking at a few examples, but I don't have a thorough understanding of what everybody is doing here.
Well, I will say that if they are in fact widespread, that should encourage folks to use more efficient approximations that aren't going to be as disturbed because they're tightly packed. That's more of a problem, right?
Yes, and that is also an area for investigation for us, because we collect data, we look at queries and so on. We can actually suggest optimizations to your index based on what we are seeing in terms of this sparsity, for example, right? These are all areas where we can actually add a lot of value, which may be much harder for customers to do at scale.
Sure.
Yeah.
Speaking of scale and performance, I mean, like, you've mentioned several times, hey, this thing scales. Like, I don't always like to get into measuring contests, but like, what are these things? What does scale mean to you all, and what do you often see for that kind of stuff?
Yeah. I mean, a couple of years back, scale would have meant to us, tens of QPS, hundreds of millions of vectors, maybe a billion vectors, and so on. If you had found a good fraction of customers who did that we would have considered that scale, because most people weren't at that scale yet. But what we are seeing is many people are at even talking about 100 billion vectors, right? That's a large scale, right? And people are growing from 1 billion to 10 billion within a year. Like they're 10xing their workloads within a year. These are all pretty big scale, right? And that's what we are seeing. What we are seeing is pretty dramatic growth in scale in the tens to hundreds of billions over the course of the coming years. Wouldn't surprise us at all if quite a few of our customers are at that scale in the next year or two. Yeah. And some of them already.
Yeah. I'm curious, right? So the other sort of side of scale is updates. And so we know that for example, when people do traditional indexing and ranking, they worry about how often to re-index, they worry about how often to retrain their models. What does that cycle look like in vector search applications?
That's a great question. First of all, in terms of actually, I should have said in terms of scale, we see two types of scale. The scale I talked about was kind of more in terms of volume. There's also scale in terms of QPS. We see kind of people just have much higher QPS workloads than they did before. To answer your question though, we see, sorry, say it again. I think somehow I forgot the question.
Well, like essentially, as new data is coming in?
Oh yeah.
What are the things? What's that maintenance cycle feel like?
Yeah. Actually, there's two aspects of that. One is, first of all, Pinecone, one of the value propositions of Pinecone, which I forgot to mention, was freshness. I should have mentioned that on it's like the first value proposition, which is we are probably the only index out there that's actually highly fresh, which means you can ingest between the point of time you ingest data to the point of time that it affects your search or appears in your search is in the seconds, less than seconds, right? Probably in hundreds of milliseconds today, right? For most users. So that's pretty fresh. But there is the other aspect of freshness, which is how often do you actually retrain your models and regenerate your embeddings and so on? People don't do that that often today. The best we have seen so far is in maybe weeks, like in a week or something like that. They do that. That's considered fairly fresh. We don't see people regenerating embeddings all that often. We do see people updating embeddings or deleting embeddings and so on. That happens fairly often, but changing the embeddings themselves or changing the model that's generating the embeddings themselves is less frequent. Yeah.
I guess from what you said, if a lot of people are using pre-trained model as is, then there's nothing to replace. Yeah.
Exactly. And the scenarios where people update embeddings often is usually around user embeddings or anything to do with recommendations and so on, right? Where the user preferences change a lot. Sense.
What do people? I don't want to. It'll come across sounding negative, but like, what do people mess up when they're implementing this? What do you see as the biggest like things where like, hey, you know, we don't do that or do the, you know, like what happens on that front?
That's a great question. I don't know if I would use the word mess up. I would say that
suboptimal. Yeah.
Surprisingly, I feel like people pay less attention to search quality than they should.
Yeah.
Meaning, they don't. I think it's also. I think that maybe educating people and making it easy, really easy for people to test and really easy for people to actually understand the quality of search that you get out of vector search systems and so on, for them to be able to know exactly what they're getting, right? I find that they do less of that than I would think they should. Partly the blame is on us in making it easy for people to do it, right? So I don't want to necessarily say they mess it up, but I do want to say that I find people doing less of that. And that's where I would spend most of my time, because unlike traditional databases and so on, where correctness is not something to even think about. Like if a database is not, traditional database is not correct, you just throw it and don't use it, right? With vector search, we are working in this world of approximate search. There is no, barring small scale data sets, you just cannot do exact search, right? So the moment you're in approximate search, the quality of search matters a lot, right? So it should be a primary factor in picking the tools you work with. And I feel like that's the area where I would say people probably don't spend as much time as they should. Because the moment you start scaling, it's very easy for people to scale these systems if they don't care about recall, right? The real challenge is to scale and keep high recall.
I was going to say, JJ asks, what metrics are important to understand?
Yeah. Often I would say it's the user metrics. At the end of the day, the ultimate customer metrics are what you should care about. some proxies for that are things like recall, right? Like that's like a very far removed proxy to the actual user metrics. So when I'm thinking about experimentation, it has to be from that point of view, which is, this technology is presumably having some impact on your business. There is a business metrics that you tie to the performance and the accuracy or recall of this system.
Yeah.
Optimize for that metric and understand how that gets affected by your choice of databases. Does that make sense? Like
it does. It does. I mean, and obviously, I mean, the other thing, I guess, which is is that, as you pointed out, you're providing a piece of core infrastructure to a larger application. And so those metrics perhaps are at a higher level.
Exactly.
So that's its own trickiness as to where you're measuring what.
Exactly.
But does, oftentimes recall and precision are trade-offs. I mean, not entirely. You can improve both precision and recall. Like, certain applications like e-commerce, et cetera, precision tends to be the thing people care about more. Like, how many did I get right in the top 10? I mean, are you still seeing those types of use cases? And
Absolutely. Which is why we don't suggest one metric here. At the end of the day, people have to have a metric that they are optimizing for. But my statement was more just about the fact that those metrics are not always that evident to people, and evident that that's like a primary choice they are making here, because the technology fundamentally approximates search.
That problem that's as old as search. Like especially engineers tend to just focus on uptime and quantity and scale and fault tolerance, and quality is a thing that you worry about later.
Yeah, you're 100% right. This problem existed even for legacy search, right? Like we find it very, very surprising when a lot of people come to us with very extensive tuning that they have done to their legacy search systems, and they just pipe data through to Pinecone and get better results. Sometimes
awesome.
Matthias has a question, different sort of integration, which is how often vector databases are really used as the feature store for other models that are being used in production environments. Something you've seen?
We see some people using us as feature stores, but very, very rarely. People use us mostly for search. Mm-hmm. They do tend to use us as feature stores because we have the side benefit. It's not something we designed for, but it's a side benefit today that you could store vectors in Pinecone and retrieve them extremely fast, especially with filtering and all this. You get the benefits of common feature stores, but it's cost effective for that purpose as well. So sometimes we find people doing this. We don't necessarily encourage it because the core value proposition for vector search is not a feature store. It's more around just better search.
I mean, I could imagine, and I don't know this is what Matthias is after, but a use case I've seen is that people would use tables for, say, retrieving things exactly. So you could imagine that this turns your table into a table that supports approximate match.
Yes. That is for sure a possibility. I don't know off the top of my head a use case like that, but I can totally imagine. Yes.
Maybe shifting gears here as we come into the home stretch, Ram, and obviously we really appreciate your time. So you're also a leader of engineering here at Pinecone, and we, of course, CoRise in this class is all about upskilling folks. Like, what are some of the key skills you're looking for in hiring engineers and data scientists? Like, for folks on this phone are like, hey, I really want to get into this stuff. What should they be learning?
Yeah. So Pinecone specifically, we hire different types of engineers. So for, we have multiple teams. Everything I talked about was kind of the core database, but there's like an experience team, which is all around the user experience of interacting with this database, data integrations, and so on. There is also relevance, which is more around how to make search better, how to improve search quality, right? So different teams have different requirements in terms of hiring. Relevance, we hire more machine learning scientists, data scientists, machine learning engineers. Our machine learning scientists typically tend to be excited about working and coming up with new algorithms for approximate search, or coming up with these algorithms that kind of provide native hybrid search, which is how do you combine traditional lexical search with dense retrieval and do it better, right, than just having two different engines. Likewise, how do you build second stage models like the re-rankers, right? How do you allow customers to kind of re-rank efficiently? with as little labeled input as possible, right? These are the sort of areas we focus on from a research point of view. We also focus on the systems research of designing these databases that are fundamentally new, right? A vector database is completely new. It has new requirements that traditional databases haven't had. So it requires systems researchers and people who really are excited about researching those areas. In terms of engineering, we had cloud infrastructure engineers. We are solving not only the problem of building a new type of vector database, we are building it cloud natively, right? Even if you look at Elastic and other search engines that have existed before, they aren't really cloud native. In fact, now Elastic is talking about building something that's cloud native. So we are solving for that problem from day one to build something that's fundamentally cloud native and scales cloud natively, right? So we hire engineers who are really passionate about building cloud native databases. And we also hire people who are really excited about accelerating search itself, like getting the most out of our modern CPUs, the most out of our modern hardware and areas like that. So like I mentioned, there's many areas we hire for. If you're interested in any one of these areas, we should definitely talk. I think it's the space of vector search is so new and so interesting that there's really innovative work to be done in all these areas.
Well, I think that tees up with what we always like to think of as kind of our closing question, which is essentially, you've seen this arc of what's happening in data and with search. What are the things that excite you most, either about what's happening now or what you see sort of around the corner in this space?
Yeah, the great question. I think the research around vector search, especially the research around sparse and dense retrieval, is maturing very fast. So are the models, so are the common understanding of how to use these models. People are getting to that curve of maturity much faster. So I think in the next few years, vector databases are really going to be the primary tool that people use for search. Right? I strongly believe it. But where we are at right now to where we need to be to kind of catch that wave, there's a lot to be done. So I think getting that science into engineering and shipping a new type of vector database that's really combines sparse and dense retrieval much better than anyone has done so far in a cost-effective manner. I think that's where I see most of the work happening. So I think it's a good time because the research is converging, engineering is getting to the point of getting enough use cases and real understanding of vector search by running things in production for years, that now we can combine the two and really build for the future.
Yeah, I think that's fantastic. I think Daniel and I probably, speaking for him as well, I mean, I think, we get this question a lot too. And it to me, at the end of the day, it's where all the money is, right? Yeah. And so if you just follow the money, then like these problems even that we talked about with faceting, et cetera, they're going to get solved.
Yeah.
The machines are going to reach a capacity, there's going to be more memory, more GPU, more everything that is going to allow those problems to be solved. And so, get on board or be relegated, right?
Absolutely. Yeah, I really believe this is the future. I think that's what's exciting to me, which is the next few years, all of this is going to shape up and we want to be at the forefront of this.
Yeah. Ram, I want to thank you so much for joining us. Any closing thoughts? And also, where can people find and learn more about you and or Pinecone?
Absolutely. Pinecone's website has plenty of information, documentation, tons you can learn from there. I am always available, so Ram at Pinecone. So feel free to shoot an email. I'm always responsive. Anything that we can help with in terms of your education or any areas that we want to focus on where you need some kind of a guidance, very happy to provide. I'm super excited to have this opportunity to talk to you all. I think it's a fascinating course, and I'm really excited that there's a lot of emphasis on vector search and these emerging areas.
Yeah, thank you so much, Ram. And for students, by the way, you've got embeddings coming out of this week's project. We're using open source search and putting them in there, but from the sounds of it, you could
use our video. Yeah.
You could just as easily send them to Pinecone. So if anybody wants to do that, go for it and let us know.
Absolutely. app.pinecone.io. And if you go there, you can sign up for a free tier with your Google account or your GitHub account.
Yeah. Ram,
awesome.
thank you so much. And in particular, thank you for not just your personal generosity here, but the generosity that Pinecone has had with sharing. We stole a couple of slides, which we've used in our class from your site. So it's fantastic explanations.
Awesome. Thanks so much. Great to be here. Thank you.
Thank you.
Yeah.